Welcome to the Future Lab. I'm your host, Matthew. Today, we're diving into a groundbreaking research paper that uses AI to revolutionize solid-state materials synthesis. This field, the combination of artificial intelligence and robotics to speed up scientific discovery, is incredibly exciting, isn't it? The research we'll discuss tackles a significant challenge in materials science. How do we intelligently select the right precursor materials and conditions to create new materials much more efficiently? We're talking about dramatically reducing the amount of trial and error that typically slows down progress. It's a huge problem because many experiments, even now, simply fail to produce the desired materials. So, what's the solution? How can we move beyond this slow, inefficient process? This is where AI steps in. This research introduces an algorithm that uses machine learning and thermodynamics to dramatically accelerate the process. We'll explore the specifics shortly, but the main idea is that this algorithm learns from every experiment, even failed ones, to better predict which combinations of materials are most likely to produce the desired outcome. And to show you just how deeply AI is transforming research, this episode's script was itself AI-assisted. Pretty amazing, right? In the next section, we'll examine the specific details of this groundbreaking research, the study by Zemansky et al., and their groundbreaking algorithm arrows. So stay tuned, let's get into the specifics of this research paper, Autonomous and Dynamic Precursor Selection for Solid-State Materials Synthesis, by Zemansky and colleagues. They're tackling a major challenge in materials science, solid-state synthesis. That's the process of creating new materials by heating and reacting solid powders, right? It sounds simple, but finding the perfect combination of starting materials and reaction conditions can be incredibly complex and time-consuming. Traditionally, it's been a lot of trial and error, which can take years and a huge number of experiments. The researchers' solution is arrows, a really clever algorithm that uses machine learning and thermodynamics to streamline this process. The core idea is that arrows learns from both successes and failures, building up a knowledge base about what works and what doesn't. It's like a smart assistant that gets better with experience, suggesting the most promising paths forward. So, how does arrows actually work? What's the process involved? Well, it starts by using a database of materials, the materials project, for example, to predict how different combinations of precursor materials would react. Then, it suggests the best-looking combinations to test experimentally, at a variety of temperatures. The experiments themselves provide key data which Arrows uses to refine its predictions. The key here is that Arrows analyzes both successful and unsuccessful experiments. It uses X-ray diffraction to determine the intermediate phases that form during each experiment. This is a clever way of indirectly monitoring the synthesis pathways. By identifying which reactions lead to unwanted byproducts, it can learn to predict and avoid those pathways in future experiments, improving the chances of making the desired material. So, it's a feedback loop. It learns from experiments and then uses this learning to guide further experiments. It really highlights the power of combining machine learning with domain-specific knowledge in materials science. That's a fascinating approach. It seems like it has the potential to significantly improve the efficiency of materials synthesis. But how does it compare to other methods? That's exactly what the researchers did. They compared arrows against traditional optimization techniques. And they found that arrows drastically reduced the number of experiments needed to find successful synthesis routes, outperforming those more traditional methods by a wide margin. This kind of efficiency is a game changer in materials science, where the sheer number of possible precursor combinations is enormous. It's a significant leap forward, and it sets the stage for our next section. We'll be looking at the practical applications and real-world impact of this AI-driven approach. Now, let's get into the nitty-gritty of how Arrows actually works. It's a multi-stage process, and it's really quite elegant in its design. First, the algorithm uses a large database of materials information, like the materials project, to make an initial prediction of how likely different combinations of starting materials are to react and produce the desired final product. This is based on thermodynamic principles. It prioritizes combinations that are thermodynamically favorable, meaning those reactions that should release energy and thus proceed more easily. Then, Arrows suggests the most promising combinations for experimental testing. But it doesn't stop there. The experiments are carried out at different temperatures, providing snapshots of the reaction pathways. This is where X-ray diffraction, or XRD, comes in. XRD is used to analyze the materials produced at each temperature. The XRD patterns tell us what materials were created, allowing Arrows to identify any intermediate phases that formed along the way. This is crucial because many reactions don't go directly from starting materials to the final product. There are often intermediate steps. These intermediates can either help or hinder the synthesis. Next, a machine learning model analyzes this XRD data to identify which pairwise reactions, essentially, interactions between pairs of phases, are leading to either the target material or unwanted byproducts. This is where Arrow's active learning aspect truly shines. If an experiment fails to produce the target material, the algorithm doesn't just discard the information. Instead, it analyzes the intermediate phases and reactions, figuring out why it went wrong. It then uses this feedback to refine its predictions. It learns to avoid reaction pathways that lead to dead ends and focuses on combinations with the strongest thermodynamic driving force toward the desired final material. This adaptive approach is what really sets Arrows apart from traditional black box optimization methods, because it's not just optimizing based on numbers, it's working with the chemical context. One of the biggest challenges the team faced was dealing with the inherent noise in experimental XRD data. Getting reliable predictions from sometimes imperfect data was critical to making this all work. But this detailed understanding of reaction pathways and the algorithm's ability to learn and adjust its strategy is incredibly powerful. And that sets us up perfectly for our discussion of the applications and broader implications of Arrows, which we'll cover in the next section. So, what are the broader implications of this research? How does Arrows change the game? The impact is huge, really. Arrows dramatically speeds up the discovery of new materials by cutting down on the time and effort needed for experimentation. This is massive for industries heavily reliant on materials innovation, think energy storage, electronics, and pharmaceuticals. In these fields, finding materials with specific properties is essential for progress. Take drug discovery, for example. Synthesizing new drug molecules is often a major bottleneck in the process. Arrows could drastically improve this by making the synthesis process much more efficient, allowing researchers to test and develop a wider range of potential drug candidates. Beyond specific applications, Arrow's success showcases a bigger picture. It shows just how far AI can go in not just analyzing data but actually guiding the experimental process itself. It's a major step toward creating truly autonomous labs. This isn't just about automating some tasks. It is about using AI to actively steer the direction of research, learning from failures as well as successes to focus on the most promising paths forward. That's a powerful idea. The fact that it worked well with different types of materials, including metastable ones, materials that are inherently unstable and difficult to work with, really highlights its versatility and robustness. It also opens the door for more research into AI-driven materials discovery. This is truly a paradigm shift. Absolutely. This paper sets a significant precedent, showing what's possible when we intelligently combine AI with traditional scientific methods. It's a very exciting development. Thinking about the future, where do you see this kind of AI-guided research going next? What are the possibilities? That's a great question. The possibilities are vast. There is room to incorporate more sophisticated models that account for kinetic factors, or to consider the influence of things like particle size and morphology which could further enhance predictions. Imagine a future where labs are largely automated, with AI systems guiding the entire experimental process, around the clock. This research brings us a huge step closer to that reality. And it really emphasizes how much of what we consider traditional laboratory work will soon be transformed by AI, which naturally leads to our concluding section. Let's bring it all together. What are the key takeaways from this research on Arrows? In short, this paper introduced Arrows, an AI-powered algorithm that significantly speeds up materials synthesis by cleverly choosing the best starting materials and reaction conditions. Arrow's strength lies in its active learning approach. It's not a simple black box optimizer. It actively learns from every experiment, both successes and failures, using that knowledge to guide future experiments. The researchers showed that it outperforms traditional methods, finding efficient synthesis routes for complex materials much faster. The algorithm's ability to learn from mistakes and incorporate thermodynamic principles and knowledge of reaction pathways shows us that systematic automation of materials synthesis is within reach. This is a huge step forward for autonomous science, promising faster and more efficient development of new materials with countless applications. It's really exciting to think about how this will change research across materials science. And looking forward, what's the next step? What future developments might build upon this research? The next steps could involve even more sophisticated AI models, perhaps incorporating factors like reaction kinetics and particle morphology to make predictions even more accurate. Integrating Arrows with fully automated synthesis platforms is another crucial direction. Imagine fully automated labs, running experiments around the clock, guided by AI algorithms like Arrows. That's the future this research points to. That's a powerful vision, and it's very exciting to consider the progress we're making in the field of AI-driven research. It's been a fascinating journey exploring arrows today. Thank you for joining us on the Future Lab. Remember, this episode's script was AI-assisted, a perfect example of the technology we've discussed. We invite your feedback and hope you'll join us next time for another exploration into the transformative world of AI-driven science. Until then, stay curious.